So you've got this machine learning problem, right? But it's just too big. Too big for one computer to handle. Well, today we're diving into a really clever solution for that exact problem. It's called MapReduce. We're going to see how it takes these massive, overwhelming tasks and just elegantly breaks them down.
I mean, this is a classic problem. You've got an algorithm, it works great on a small data set, but now your data is enormous. A single machine could take days, maybe even weeks to get through it all. So what do? How do you scale this thing up without waiting an eternity for it to finish?
And a lot of the time, the bottleneck is something that looks just like this. Now, don't worry about all the crazy-looking math here. Just focus on that big Greek letter, the sigma. It just means summation. It means the algorithm has to loop over every single example in your training set just to take one tiny step forward. And when you have millions of examples, well, that becomes a huge, huge problem.
Okay, so let's really wrap our heads around this bottleneck. Let's put some real numbers to it so we can see the scale of the challenge we're facing. I mean, sure, 400 examples? No problem. A single computer can handle that. But what if it's 400 times million examples? All of a sudden, that simple summation turns into this computational monster. Your computer just can't churn through that amount of data in any reasonable amount of time. This is where we need to start thinking differently.
And that new way of thinking, well, it's actually one of those beautifully simple ideas. It's a classic strategy you might have heard of before, divide and conquer. And it completely changes the game. And it's called MapReduce. The core idea is basically this. You take a giant problem, chop it up into smaller, bite-sized pieces, you process all those little pieces at the same time on different machines, and then you just combine the results at the end. It's a way to harness the power of a whole team of computers to solve one massive problem.
And you know, we have a couple of legends to thank for this idea. Jeff Dean and Sanjay Gamawat at Google. They originally developed this to handle the absolutely mind-boggling amount of data that Google deals with every single day. And in the process, they pretty much revolutionized large-scale computing for everyone.
Okay, that's the theory. But how does this actually work in practice? Let's walk through it step by step. It's actually pretty intuitive.
It really boils down to these three main steps. First, you split your massive dataset into manageable pieces. Then you map your calculation, that summation we were talking about, across all those pieces at the same time. And finally, you reduce all the partial results back into one single final answer.
Visually, it's super simple to understand. You just take your big training set, chop it up, and you send each one of those chunks to a different computer. So instead of one poor machine trying to do all the work, you now have a whole team of computers, and each one is just working on its own little piece of the puzzle.
And this is where you really see the magic. That one machine has to struggle with all 400 million examples. But with 4 machines, each one only has to worry about 100 million. Now, in a perfect world, that's a 4 times speed up. Realistically, you've got some network chatter and overhead, but still, it is a huge, huge win.
So let's look at how that final combination step actually works. Each machine crunches its numbers and comes up with a partial sum. You can call it temp 1, temp 2, and so on. These little pieces of the answer are then sent over to a central server, and its only job is to add them all up to get the final result. The answer is identical to what the single machine would have gotten, it just gets there way, way faster. So yeah, this is fantastic for gradient descent, but the really cool thing is this underlying idea, this secret sauce of using summation, it applies to so many other algorithms out there.
This is the golden rule right here. This is the question you need to ask yourself if you want to know if MapReduce can help you. If the heavy lifting, the computational core of your algorithm is just a big sum over all your data, then this approach is almost certainly going to be a great fit.
And guess what? A ton of common algorithms fit this exact pattern. Take logistic regression, for instance. To make it work with advanced optimization techniques, you need to calculate both the cost and the gradient. And would you look at that? Both of them are just big sums over the training set. These are perfect candidates for MapReduce.
Okay, so you might be thinking, this is great, but I don't have a giant Google data center in my garage. Well, here's the best part. You don't need one. You can use this exact same idea on the machine that's probably sitting on your desk right now.
That's right. The computer you're using right now almost certainly has multiple processing cores. A quad-core CPU, that's kind of like having 4 mini-computers packed into one chip. And you can use the exact same MapReduce logic to split the work between those cores instead of between different computers.
And just look at this comparison. It makes it so clear. On one side, you have a data center with a bunch of different machines. On the other, you have your desktop with a bunch of different cores. The principle is exactly the same. Divide the work and conquer the problem.
The huge advantage of doing this on your own machine? No network lag. Since everything is happening inside one box, the communication between cores is almost instantaneous. This can give you a really dramatic speedup. And the best part? A lot of modern programming and linear algebra libraries are smart enough to do this for you automatically behind the scenes.
So what does this all mean? It means that this whole approach, this MapReduce way of thinking, it's not just some theoretical concept for giant tech companies. It's a powerful tool that brings parallel computing from those massive data centers right down to your desktop. It lets us tackle data sets that used to be completely out of reach. So the only real question left is, with all this power at your fingertips, what massive problems are you going to solve?